Hello everyone, good evening. I am Rahul Patel from Department of Chemical Engineering from IIT Bombay, and I will be conducting this live sessions to solve the past year gate questions. I hope I am audible, and I think we will start the discussion once few more people arrived. So we can start it around 7:05, 7:10. We can wait till then. So I guess it's 7:05, so we can start our discussion. So we will be solving. I hope I'm audible. Just can anyone write in chat if I'm audible? Okay, thanks, Ispo. So we will be solving the questions of heat transfer subject in this discussion in this live session from 7 to 8 every Tuesday. So this will be past year gate questions. So earlier we had solved the questions, few of the questions from 2007 as well as 2022 paper, and today we will be looking into the past questions of 2021 paper. So I will be discussing the concepts that will be used to solve these questions in short, and then we can move on to the video discussions of that question. Meanwhile, if you have any doubt, you can just write it in chat box or unmute yourself and speak. Okay, so let's start with the first question. So the first question is question number 7 of GATE 2021 paper, and the question is, in a double pipe heat exchanger of length 10 meter, a hot fluid flows in the annulus and a cold fluid flows in the inner pipe. The temperature profile of hot and cold fluids along the length of heat exchanger x is greater than 0 are given by this equation, where TH and TC are in degrees Celsius and x is in meter. And we have been asked to find the log mean temperature difference. Okay. The related course theory can be found out in these two links. So one is video lecture and the other is web lectures. So here we have been given double pipe heat exchanger, and a hot fluid flows in the annulus. Annulus means on the outer side of this pipe, and the cold fluid flows in the inner side of this pipe. Okay, so the cold fluid flow from here, and we have been given the temperature profile along x. So this we can consider as x, and we have been asked to find the log mean temperature difference. So usually if the temperature profile is varying across x, then we calculate this log mean temperature difference to find the average of temperature difference across each of these. So this LMTD is defined as delta T1 minus delta T2 upon ln of delta T1 upon ln of delta T2, where delta T1 is my temperature difference at this point and delta T2 is the temperature difference at this section. So we will use that concept to solve this to find the log mean temperature difference. So let's just take a look on the video solution of this question. Just let me know if the video. Hello everyone, audio is not audible. We will be solving question number 7 of GATE chemical engineering paper, and the subject is related to heat transfer. The question is, in a double pipe heat exchanger of 10 meter length, a hot fluid flows in the annulus and a cold fluid flows in the inner pipe. The temperature profiles of the hot TH and cold TC fluids along the length of the heat exchanger x such that x is greater than 0 are given by these two equations, where TH and TC are in degrees Celsius and x is in meter. The logarithmic mean temperature difference in degrees Celsius is, so we have an MCQ type of question, and we have been asked to find the log mean temperature difference LMTD for this double pipe heat exchanger. Okay, so here we are having double pipe heat exchanger. So let's just make a schematic of that. And the hot fluid flows in the annulus and cold fluid flows in the inner pipe. Okay, so this is my TC, and let's just consider the hot fluid enters from this side. Okay, so this kind of flow is known as co-current. If it enters from the opposite direction, then it is known as counter current. Okay, and we have been given the temperature profile. So from the temperature profile for this hot fluid that flows in the annulus, we can see that the slope of that line is negative. That means if I keep on increasing x, then TH decreases. Okay, so if this is my x direction, okay, so if I am increasing x, then the temperature of hot fluid will decrease as per this equation. And so if we are considering the co-current flow, then that would satisfy. That is, as I move along the pipe, the temperature of the hot fluid will decrease. So that is why we are taking it as co-current. If we had taken it as counter current, then the slope should have been positive. Okay, so that is why we are taking a co-current flow. Okay, so if I had to draw temperature profile, I can draw it as, this is my x in this direction, so For the hot fluid, the temperature is decreasing, so this is my TH. And for the cold fluid, the temperature is increasing, so this will become TC. Okay, now we have this log mean temperature difference definition as delta T1 minus delta T2 upon ln of delta T1 upon ln of delta T1 upon delta T2, where delta T1 is my temperature difference. You can take it as at inlet, and delta 2 is temperature difference at the outlet. Okay, so let's just find in general delta T at any x. Okay, so that will be temperature of the hot fluid at x minus temperature of cold fluid at x. So it will become 80 minus 3x minus of 20 plus 2x. You can solve this and it will become 80 minus 20 is 60 minus 3x minus 2x is minus of 5x. Okay, so my delta T at any x is 60 minus 5x. Now for delta T1, x1 is x is equal to 0. So we will be getting delta T1 is equal to 60 minus 5 of 0. So we are considering right now this point, that is my x equal to 0. So it will become 60. Similarly, for delta T2, we can take x equal to the L, and we have been given the length as 10 meter. Okay. So this is 10 meter. Similarly, delta T2 will become 60 minus 5 into 10. It will become 60 minus 50 is 10. Okay, so we have delta T1 and delta T2. Based on that, we can calculate my log mean temperature difference. Okay, so delta TL is equal to delta T1 minus delta T2 upon ln of delta T1 on delta T2. So delta T1 was 60 and this is 10. Okay, so it will become 60 minus 10 upon ln of 60 upon 10. It is 50 upon ln of 6. So you can solve this using the calc, and this value will come around 27.9. So our log mean temperature difference is 27.9 degrees Celsius. So from the given option, our B option is correct, 27.9 degrees Celsius. Okay, so we looked upon these questions covering the basics of log mean temperature difference. And if anyone of you has doubt, then just write it in chat box or just speak up, or else we can move to the second question. Okay, so I think you don't have doubt, so we can move on to the second question. So in the second question, we have been given a silent to heat exchanger and a clean overall heat transfer coefficient, and it is expected that the heat exchanger may be fouled during the operation, and the fouling resistance of 0.01 meters square Kelvin per watt is prescribed. So we have to find the overall heat transfer coefficient when the heat exchanger is dirty. So let's look at the video solution of this question. Hello everyone. We will be solving question 8 of GATE Chemical Engineering paper 2021 from the subject of heat transfer. The question is, For a shell and tube heat exchanger, the clean overall heat transfer coefficient is calculated as 250 watt per meter square Kelvin for a specific process condition. It is expected that the heat exchanger may be fouled during the operation, and a fouling resistance of 0.001 meter square Kelvin per watt is prescribed. The dirt overall heat transfer coefficient is in dash watt per meter square per Kelvin. And this is an MCQ type of question, and we have been asked to find the overall heat transfer coefficient considering the fouling in the shell and tube heat exchanger. So from we know that if a heat exchanger has been running for a long time, then due to maybe corrosion or scaling, it will develop a layer, and that we call it as fouling. So that decreases the performance of cell and tube heat exchanger. So basically, this scale adds a resistance to this heat transfer. So if I'm having a clean heat exchanger that is on the start of my operation, when the heat exchanger has been initially used, then the heat transfer coefficient, then the heat exchanger would be much faster as compared to when the scaling has happened. Okay. So for the resistance due to scaling, we have the formula as, so let's just write this R as resistance due to scaling is equal to 1 upon heat transfer coefficient of the fouled heat exchanger minus 1 upon heat transfer coefficient due to of the clean heat exchanger. Okay, so this is my resistance, and these are my overall heat transfer coefficient for clean HE and for the fouled heat exchanger. And here we have been asked to find the dirt overall heat transfer coefficient, that is this we have to find. And here we have been given the fouling resistance of 0.001 meter square Kelvin per watt. So we can write this as 0.001 is equal to 1 upon UF minus 1 upon the clean overall heat transfer coefficient is 250 watt per meter square Kelvin. Okay, so we can write this as, okay, so this will become 0.004 UF will become 1000 upon 5. So this is 200. So my dirt overall heat transfer coefficient in this case is 200. So you have to remember this basic formula for the calculating the resistance due to scaling. And from the given options, we can select this 200 as our final answer, 200 watt per meter square. Yes. So this was a very short question in which we had to find this overall heat transfer coefficient based on this dirty heat exchanger. So that was a very straightforward application of the formula. And now we can move on to the next question. So this is question number 46 of GATE 2021 paper, and it is a numerical answer type question. So the question is, a straight pin of uniform circular cross section and the adiabatic tip has an aspect ratio length by diameter of 4. If the Biot number based on radius of the fin as a characteristic length is 0.04, the fin efficiency is dash percent. So here we have been given the aspect ratio of 4 and the Biot number based on radius. So this is an important information. So we have to calculate the Biot number based on the radius of the fin as the characteristic length, and that we have been given as 0.04. And we have to find fin efficiencies. So let's look at the video solution. Hello everyone. We will be solving question 43 of GATE 2021 Chemical Engineering paper, and the subject is heat transfer. The question is, a straight fin of uniform cross-section and adiabatic tip has an aspect ratio length upon diameter of 4. If the Biot number based on radius of the fin as characteristic length is 0.04, the fin efficiency is dash percent. This is a numerical answer type question, and we have to answer on the basis of it, round off to nearest integer. So in this question, we have been asked to find the fin efficiency. So fin is you might know that fin is an extended surface that is used to increase the heat transfer. Okay, so basically, if I provide the provide the fins, then the heat transfer would be much efficient, and that would help in either more efficient heating, more faster and efficient heating or cooling, whatever is our main purpose. Okay, so there are two main parameters related to fin efficiency or effectiveness. So here they are defined as the fin efficiency is actual heat transferred divided by heat which would have been transferred if the entire fin were at base temperature of the body. Okay, so if my body's temperature is Ts, so at 100%, so yes, the heat that would have been transferred if the entire fin were at base temperature of the body. That means this entire fin should be at Ts. So if such is the case, my heat transfer would be very much efficient. And then the other performance factor is the fin performance. It is defined as the rate of heat transfer with fin and rate of heat transfer without fin. So in absence of fin, what would have been my rate of heat transfer? So that can be captured using this fin effectiveness. But in our question, we have been asked to find the fin efficiency. Okay, so we have to use this concept, fin efficiency. Okay, so we define this fin efficiency as NF is equal to actual heat transferred upon Q if the heat transfer of the entire fin were at base temperature. If fin is at base temperature. Okay, so in this question, we have been given a straight fin of uniform cross section, uniform circular cross section. So we are having basically we are having a cylindrical fin over here. And let's just consider that diameter of that fin is D and length is L. Okay, so here we have been given it has an adiabatic tip. That means no heat exchange occurs through this surface. So here delta Q is equal to 0, and we have been given L by D as 4 aspect ratio. And if the Biot number based on the radius of fin as characteristic length is 0.04, okay. Here we have been asked to use the radius of the fin as characteristic length. So that will become, so my Biot number is defined as Hx upon K. So it will become HR upon K is equal to 0.04. So later on we might be needing this, and we have been asked to fin efficiency. So for a cylindrical fin, you would have remembered the equation of the heat transfer if we are having a cylindrical fin. So that is given as under root of H. H is my heat transfer coefficient. P is the perimeter. Okay, so in this case, the perimeter will be pi d. Then K is my thermal conductivity. A is the area across which my heat transfer would. A is the cross section area. Okay, so it's the thermal conductivity. Okay, so area will become pi d square by pi r square. So that is basically pi d square by 4. So this is the first parameter, and the temperature difference. So if my fin is at so if my wall temperature is TW and the ambient temperature is T infinity, then we can write it as TW minus T infinity, and then we have a factor of hyperbolic 10 ml. So you have to remember this formula for any of the fin, that is under root of HPKA, then the temperature difference, and 10 hyperbolic ml. So this is my heat transferred in presence of fin. Now heat the Q if the fin is at base temperature. So for the idealistic case, it will be basically HA delta T, and the area of the heat transfer area would be this 2 pi RL. Okay, 2 pi RL is basically my perimeter into length. So okay, so that I can write it as perimeter plus H into P into L, then my temperature difference TW minus T infinity. So this is my fin efficiency. So from here you can just cancel these terms. Fin efficiency will be given as sorry for that. Fin efficiency will be given as under root of HP KA upon HPL under root of 10 hyperbolic ml. So I think you can cancel this HP, so it will become under root of KA upon HP into 1 upon L into 10 ml. Okay, so we will be using this formula to calculate the fin efficiency. So yes, so from here you can see that this m factor is, we define it as under root of HP upon K. Okay, this is my m. So if we replace this under root of HP by K over here, then we can get it as 10 hyperbolic ml upon this will become 1 upon m, and this is 1 upon L already, so it will become this. So my final heat effectiveness factor is 10 ml upon ml. So you can straight away remember this equation for this fin efficiency. Okay. So what information we are having, the fin efficiency is given as 10 hyperbolic ml upon ml, and the other thing we are having HR upon K is 0.04. HR upon K is 0.04. The other thing we are having is L by D is 4. So to find this efficiency, let's just calculate this m first. Okay. So m is given as under root of HP upon KA. So for the fin, the perimeter we discussed it as pi d, and area as pi d square by 4. So I will just replace those values over here. P is pi d, K into area is pi d square by 4. So pi will become cancelled. 4H d upon K. No, not this. So d will be denominator 4H upon KD. Okay, so now let's just find this ml term. Ml will become length into 4 h upon kd. Now here we are having this hr upon k as 0.04. So from here we can get this hd upon k will be twice of that term. So basically 0.04 into 2 will be 0.08. Now I need to fit this equation over here. So what I will do is I will just multiply and divide this under term with diameter. Okay. So now I am having hd upon k. Okay. So this term I am having, and this d square I will take out of the square root bracket. Under root of 4 into hd upon k, I am already having it as 0.08. Okay. And L by D I am having it as 4. So 4 into under root of 0.32 is my ml. So you can calculate this, and the ml value will come around, I think, 2.262. We will put this ml value in this equation, and we can get effectiveness factor as hyperbolic 10 of 2.262 upon 2.262 is equal to, so this will come around 0.978 upon 2.262, so it will become 43. So it will become 0.4324, and we have been asked to write it in percentage, so our final answer will be 43.24%. So since we have been asked to round up to nearest integer, so we can write it as 43 or 44. So this will be my correct fin efficiency in percentage. Okay, so if anyone has doubt, then they can ask. Basically, in this question, we calculated the fin efficiency of a fin of circular cross section. So you can straight away remember the formula to calculate the fin efficiency, as fin efficiency will be given as 10 hyperbolic ml upon ml, where m is given as under root of hp upon ka, and you should remember that k is the thermal conductivity of the fin, h is my heat transfer coefficient, p is the perimeter of the fin, whereas a is the cross section area of the fin. So this thing you can remember, and you can just straight away use this formula to find the fin efficiency. I will wait for, I think, 1 or 2 minutes. If you have any doubt, then you can ask. Then we can move on to other question. So this is how we define the fin efficiency and fin performance or effectiveness. Both are different measures to calculate the performance of the fin. So in our question, the answer was 43.24%, and since we have been asked to round off till nearest integer, the answer can lie within this range, 43 to 44. Okay, so now let's look at another question. So this question is basically based on this evaporation section of heat transfer subject. And here we have been given a double effect evaporator that is used to concentrate a solution. Then steam is sent to the first effect at 110 degrees Celsius, and the boiling point of the solution in the second effect we have been given as 63 degrees Celsius. We have been given the overall heat transfer coefficient of first and second effect. Then there are some basic assumptions, and we have to find the temperature at which solution boils in the first effect. So let's look at the video solution of that question. Hello everyone. We will be solving question 44 from GATE 2021 Chemical Engineering paper, and the subject is heat transfer. A double effect evaporator is used to concentrate a solution. Steam is sent to a first effect at 110 degrees Celsius, and the boiling point of the solution in the second effect is 63.3 degrees Celsius. The overall heat transfer coefficient in the first and second effect are 2000 watt per meter square Kelvin and 1500 watt per meter square Kelvin respectively. The heat required to reach the temperature of feed to the boiling point can be neglected. The heat flux in the two evaporators can be assumed to be equal. The temperature at which the solution boils in the first effect is degree Celsius. So here we have been given double effect evaporator, and we have been asked to find the temperature at which the solution boils in the first effect. So basically we have been asked to find the outlet temperature of the vapors of the first effect Okay. So just to give a basic schematic of a double effect evaporator, so it will so this is my first evaporator. If I'm only using single one, then it is single effect evaporator. Since I'm using two evaporators, we call it as double effect evaporator. Okay, so here we have been asked steam is sent to first effect at 110 degrees Celsius. Okay, so I can write this Ts as 110 degrees Celsius, and the boiling point of the solution in the second effect is 63.3 degrees Celsius. So for this is my first effect evaporator, this is my second evaporator, and since the boiling point is 63.3 degrees Celsius, the vapor will leave at boiling point. Okay, so let's just consider the outlet of this evaporator. Here it will be T1 and here it is T2. So T2 we have been given as 63.3 degrees Celsius, and we have been given the overall heat transfer coefficient in first and second effect. Okay, so here U is equal to 2000, and in this U1 is equal to 2000 and U2 is equal to 1500. Okay, and the heat required to raise the temperature of feed to the boiling point can be neglected. Okay, the heat flux of the two evaporators are assumed to be equal. So okay, the for for, for first evaporator, if the heat flux is Q upon A1, so that will be equal to the heat flux of the second evaporator. Okay, this we have been given. The temperature of this solution boils in the first effect. So basically we have been asked to find T1. So we will just write the heat balance across each heat balance across these two equations using this information that has been already provided. Okay, so based on this overall heat transfer coefficient, we can write Q as UA delta T, where delta T will be my inlet minus outlet temperature. So for first effect evaporator, the inlet temperature is 110 and the outlet is T1. Similarly, for second, this vapor is going into the inlet stream. Okay, so for second, the delta T would be delta T1 minus of delta T2. Okay, so that we will write over here U1 delta T1 is equal to U2 delta T2. U1 we have been provided as 2000. For the first effect, we have been given delta T1 as 110 minus T1. Similarly, 1500 into delta T2 will be this T1 minus T2. Okay, so we can just write this as this becomes 220 minus 2 T1 is equal to 1.5 T1 minus of 1.5 T2. Okay, and in this case we have been given T2 as 63.3. So it will become 1.5 T1 minus 1.5, 63.3 degrees Celsius. So basically that will become 2 plus 1.5 is 3.5 T1 is equal to 220 plus 1.5 into 63 will be 94, will become 94.95. 94.95 degrees Celsius. So that will imply T1 will become and this will come around 90 degrees Celsius. Okay. So if the temperature at which the solution boils in the first effect is around 90 degrees Celsius, so that is our final answer, 90 degrees Celsius. Since we have been asked to round up to nearest integer, we will report the answer as 90. So if you have doubt in this question, then you can just speak up. In this, we looked at the concept of this double effect evaporator and basically calculated the heat balance across both of this effect to find the temperature at which the solution boils after the first effect. Yes. So we can move on to another question. So in this question, we have been given a solid slab of thickness 2L and uniform cross section A. We have been given the volumetric rate of heat generation and some assumptions, and the temperature profile within the slab is given, and we have to find the maximum temperature in the slab. So we can take a look on the video solution of this question. Hello everyone. We will be solving question 45 of GATE 2021 chemical engineering paper, and the subject is heat transfer. The question is, consider a solid slab of thickness 2L and uniform cross section A. The volumetric rate of heat generation within the slab is G dot, and the units are watt per meter cube. The slab loses heat by convection at both ends to air with heat transfer coefficient H. Assuming steady state one-dimensional heat transfer, the temperature profile within the slab along the thickness is given by this equation, where K is the thermal conductivity of the slab and Ts is the surface temperature. If Ts equal to 350 Kelvin, ambient air T infinity equal to 300 Kelvin, and Biot number is 0.5 based on LS characteristic length, the maximum temperature in the slab is dash Kelvin, round off to nearest integer. Okay, so we have to find the maximum temperature of the slab given this temperature profile and all those other parameters. So let's just draw a schematic diagram. Here we are having a solid slab of thickness 2L, and here we have been providing it goes from minus L till L. Okay, so this will be minus L and this will be plus L, and cross section area A. So this will be my cross section area A. And the volumetric rate of heat generation is G dot. So this is my volumetric rate of heat generation. The slab loses heat by convection both ends to air with, so here we are having air, both ends the heat transfer coefficient is H. Again, Ts is the surface temperature and Ts has been given as 350 Kelvin, and ambient air we have been given it as T infinity, that is 300 Kelvin. The maximum temperature of the slab is, okay, so we have to find what is my maximum temperature. So first we have to find at which point the maximum temperature will lie. That is the x corresponding to T max. So since this slab is symmetric, we can say that the temperature will be maximum at the center. So that is at x equal to 0. So since x varies from minus L to L, that is x equal to 0, this will be my center, and at this point the temperature will be maximum. Also from this equation, so that is temperature is a function of 1 minus x square. So this is the equation of parabola. Okay, so if this is my x, then the temperature profile within the slab will vary in the parabolic form, and this will be my T max. You can also find the location of the maximum temperature by differentiating this equation and equating it to 0. So let's just check that. Okay, so Tmax is given as g dot L square upon 2k plus Ts. And if I had to, no, so this is only T. So for T equal to Tmax, this del T upon del X should be equal to 0 at T equal to Tmax. Okay, so we can differentiate this and equate it to 0, so it will become, so differentiation of 1 is 0 minus this is kind of x square, so it will become 2x, and then we'll use chain differentiation to differentiate this, so it will become 2x upon L into differentiation of x with respect to x will be 1 into 1 upon L plus this will become 0. Okay, so here we will get 0 equal to, this will become 0, so it will become minus of 2x upon, so this was 1 minus of 2x upon L square. Since we know that length is a finite term and it is not equal to 0, so this equation will only satisfy at x equal to 0. Okay, so yes, from here we can see that at the center the temperature will be maximum. Now if I had to find the maximum temperature, I will just put x equal to 0 in this equation, and we can get T will be T max g dot L square upon Tk upon 2k, and this, if I put x equal to 0, so this entire term will become 0 into 1, and then we are having this Ts term. So this is my maximum temperature that we have been asked to find. So now we need to find all these parameters and replace it into this equation to find the maximum temperature. Now since we don't have this g dot, we will write this heat balance across this entire slab. And the heat balance, you can always write it as rate of accumulation is equal to heat input minus heat output plus generation. Now here rate of heat accumulation will be 0, input to the given system is also 0, and the output will be, so since the heat is generated and here there is air, so convection will occur through this slab, so we can write the output as twice of the heat that has been conducted to a single layer. So since there are two surfaces, one on this side and another on this side, so we will write the heat transfer due to convection as twice of HA delta T. Okay, and delta T in this case would be my surface temperature minus the temperature of ambient, that is Ts minus T infinity, plus heat generation term we have been given as G dot, and this is watt per meter cube, so we have to change it into watt, so we'll just multiply it by the volume of the slab. Okay, so G dot into the volume of the slab will be area into 2L. Okay. So from here we can find the desired term that are to be used in the previous equation. So we can just cancel 2A. This will give us G dot L is equal to H into Ts minus T infinity. Ts we have been provided over here, that is 350, and T infinity is 300 Kelvin. It will become 350 minus 300 is equal to 50H. Okay. And we have also been provided this Biot number as 0.5. Let's just write it over here. Biot number is 0.5. Now Tmax we have already found using this equation, that is GL square upon 2K plus Ts. Now, so Biot number we have been provided as 0.5, and we have been used asked to find this characteristic length. This length is characteristic length, so this will become HL upon K. Okay. So now I will be replacing this GL in this equation, so it will become 50H into this GL into L, and that's 50H into L upon 2K plus Ts. And now we'll be using this equation into here, that is HL upon K we have been given as 0.5. It will become 50 into 0.5 upon 2 plus Ts. So it will become 25 into 0.5, that is 12.5. Plus temperature of the surface we have been provided as 350. So that is 362.5, and the units were Kelvin. Okay, so the maximum temperature we have found out as 362.5 Kelvin. So yes, since we have been asked to round up to nearest integer, we will write the answer as 363 Kelvin or 364 Kelvin. Okay, so we looked upon this question involving the heat generation across this a solid slab of thickness 2L and calculated the maximum temperature within this slab. Yes, if you have any doubt, then you can ask me. I will just wait for the next 5 to 6 minutes, or else we can end this call. So today we looked upon 5 questions. So let's just revise those again. So the first question was based on this LMTD, in which we were asked to find the log mean temperature difference given the temperature profile of hot and cold fluid. So from the slopes of both of this hot and cold fluid, you have to figure out whether this is a counter current heat exchanger or co-current heat exchanger. The other question, in which we were asked to find the overall heat transfer coefficient based on the dirty heat exchanger. So this was a straightforward equation that was to be used. In the third question, we had to find the fin efficiency for a fin with circular cross section. You can just straight away remember this formula for fin efficiency as this 10 ml upon hyperbolic 10 ml upon ml to find the fin efficiency. Then in the fourth question, we looked upon this concept of double effect heat evaporator and did the heat balance across the double effect heat evaporator, find the temperature with the solution boils. And in the last question, we did this heat balance across this solid slab of thickness 2L to find the maximum temperature within the slab. So if you have any doubt, you can ask. I will just stay here for 5-10 minutes and then we can end the call. I'll just stop sharing my screen, and if you have any doubt, you can ask. Next time also we'll be looking into this heat transfer question. If you have any doubt, you can just write in chat box or just speak up. If none of you have doubts, then we can end this call. And thank you everyone for attending. You can leave the call if you don't have any doubts. Okay, so I think none of you have doubts, so we can end today's call. Okay.